So so today I want to talk more about summation notation and stuff with summation. Okay. And so when you're done with your note card, just turn it in to the front. Anyone still have a note card out? Yeah. I did not grade them. So this is graded by a grader, and I think the grader just graded the first three. Yep. Yep. Okay. So so today we're going to talk about summation notation. So to cover some of our bases. So summation stuff. Okay, so sums are a lot like integrals. So given a function f and two natural numbers, let's say integers even, a, b, then we can define this thing here, this sum symbol. So this runs from a to b. So this thing here, so if I write this as f of j, this is equal to f of a plus f of a plus 1, all the way up to f of b. Okay? So this is very similar to an integral, right? The integral of f of x from a to b dx. Okay, so this is the notation is really similar. So how is it similar? Okay, so in the same way that so this is maybe for summation, and then we do like a little integration. Okay, so j is a dummy variable. And in this thing, x is a dummy variable. So the integral from a to b of f of x dx, this is the same thing as the integral from a to b of f of y dy. Right? In the same way here, the sum from j is equal to a up to b of f of j is equal to sum from j is equal to, let's use k, equal to a up to b of f of k. So these two things are the exact same. Okay? It's also linear, right? So they're both linear. So this one's also linear. And by this I mean that the integral from a to b of c times f of x dx plus the integral from a to b of g of x dx. So this is equal to the integral from a to b of c f of x plus g of x dx. On this side, you could do the same thing. J is equal to a up to b. If I do a constant here, f of j plus the sum from j is equal to a up to b of j here. This is really equal to the sum from j is equal to a up to b of c f of j plus g of j. Right? So you can kind of collect the stuff on the inside. Okay, so this is what it means to be linear. Okay, so c is a constant there. You can also separate. You can also separate integrals. So I'll continue this thing. So you can break them up. Okay, so I'm going to use c again, but this time it was a constant. So you can also break up integrals. Break them up. So here, the integral a to b of f of x dx, this is the same thing as the integral from a to c of f of x dx plus the integral from a, or from b, or from c to b of f of x dx. So this is for c in between here, a and b. Okay, in the same way here, we can also break up. So I'm not going to have good space here, so I'm going to do it over here. So for sums here, right, you can also break them up. So if I had a sum, so given c in between with here, we're going to have two integers, a less than or equal to b here. Then this sum here, j is equal to a up to b of f of j. So this sum looks like the following. It looks like, well, f of a plus f of a plus 1 plus all the way up to f of c plus f of c plus 1 plus so on, plus f of b, like this. So this can actually be broken up into two pieces. You can do this first piece here, from a up to c, and then you can do c plus 1 up to b. Okay, so let me kind of continue this. Right, so this is equal to the sum from j is equal to a to b of f of j, or sorry, up to c, plus the sum from j is equal to c plus 1 up to b of f of j. Okay? Does that make sense? So like you're in the same way that you break up an integral into two pieces, you can break up a sum in the same way. And so this is often used, so let me just make a remark. This is often used for, peeling off the beginning term, the starting or ending term, or ending term of a sum. Okay, and then I'm going to show how to work with this a little bit. I want to do the binomial formula example from your homework. I'm not sure I'll get to it, but maybe at the beginning of next class I'll do it. But I'm going to show you how to work with these a little bit more. Okay, and so another remark is that instead of writing fj here all the time, we often use constant symbols. So instead of writing a notational thing, so instead of writing using fj, we often use subscripts instead. Right? So like alpha j. Like, aj or bj or alpha j, etc. And I just want to warn you that these a's here have nothing to do with these beginning and starting terms. And usually this thing will start at 0 or 1, and then this is kind of a variable that we leave here. It's usually like an n or a capital N or an m. So we use i's, j's, and k's. We use i's because it's for the letter index, so I, and then we have j and k, and they come after, so we use j's and k's as well. So it's a pretty common thing. All right, and so I'll talk a little bit about reindexing when I do the binomial Formula 1. For now, I just want to give you some famous examples that I think you guys should know. So famous examples of sums. Okay. Okay, so I'm going to start with the sum of n numbers. And maybe you guys have heard this story. Okay, so so there is a story. So let me just tell you the theorem. Okay, so here's the theorem. Okay, and it says that the sum from k is equal to 1 up to n of k. Okay, this thing is just equal to n times n plus 1 divided by 2. So we were doing this a little bit with induction, but I want to give you guys the proof here. So let me just tell you a story first. Okay, so this is kind of a famous story. This formula, I think, was known to the Greeks. So it's very old. But there's kind of a Gauss story, right? So let me just kind of, I'll just do this. So so here's the story, okay? So when Gauss was in 4th grade, right, his teacher wanted to give him a bunch of busy work, okay? And so what they had them do is they had them add the numbers 1 through 100. So the question was, so we'll add all these numbers, and then they had them add all these numbers, and they wanted to figure out what this was, okay? So they were like, S was equal to what? Okay, and so Gauss, being a clever 4th grader, right, what he did was he did the following, right? By the way, these stories always have a different version depending on what country you're from. So there's probably a Chinese version of this story too, okay? So yeah, and I'm sure there's an Arabic one, and well, where Al-Khwarizmi did it, and so on and so forth, okay? So this is not, it's probably not a historically accurate story, okay? So so what Gauss did, okay, was he took these numbers, right, and then he realized that if you, so that there's a trick here. If you take these numbers and you rearrange them, so 99 plus 98 plus dot 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 plus 1, this is also equal to S, okay? And so what you can do is you can, add these two things together, okay? And this trick only really works for this sum, okay? But you can add these together, and then you get 101 plus all the way up, and then you get, this one's 101, this one's also 101, and this one's also 101, okay? And this thing is 2 times S, all right? So this number here is actually, well, there's 100 numbers, and they're all 101. So this is 100 times 101. Okay? So, so what does this tell us? So this tells us that S well, this is 100 times 101 divided by 2. So this is just 50 times 100 plus 1, which is 5,000, plus 50, which is 5,050. Okay, and so they had their little tablet, and then Gauss just kind of like threw his chalkboard on the floor with that number, right? And then the teacher was in shock or something. Okay, so that's the Gauss story. Okay, anyway, this is how this proof works. This trick works in general. Okay, so the proof in general, it's the exact same thing. So here's the proof of this is the sum of n numbers. Okay, so 1 plus 2. All right, let's do this. So this sum here, j is equal to 1 up to n. So this is of j. So this is 1 plus 2 plus so on up to n. Okay, and we can call this, we can have this defined to be equal to s. Okay, and so we can add the same thing. So this is equal to n times n minus 1 plus all the way up to 1. This is also equal to s. So adding these together gives the following, that so 2s is equal to n, and then times n plus 1. All right, and this allows us to show that s is equal to n times n plus 1 divided by 2. All right, we could have also proved this by induction, right? But, and that's by peeling off the terms, right? But here, this is kind of a direct proof of this one. And I think you guys should know this proof. Okay, so this is kind of a famous proof that everyone taking this class should know. All right? Okay, so now you've heard the Gauss story. This is an n plus 1 here. This is an n. This is an n minus 1. So we're doing n minus 1 plus 2, right? Maybe it's instructive to do this with notation, right? So maybe in summation notation, right? So we really have this thing. So 2s is equal to, well, 2. Well, let me just write it like this. J is equal to 1 up to n of j plus the sum. J is equal to 1 up to n. And this is also j here. But the trick was to observe that 1 to n plus of j plus the sum. And then I'm going to do n minus j like this. So that was the trick, is that these two things are the same. Okay, and then you can add them together. Sum of j is equal to 1 up to n here. And now you have j plus n minus j. Okay, so that's one way of writing this. And so this is equal to, so this is equal to the sum here from j is equal to 1 up to n. And then this is here n. Okay, because we're just adding and we're subtracting j. Now this doesn't involve, this thing here doesn't involve any j's in it, right? So by linearity, we can pull it out. J is equal to 1 up to n of j, or sorry, of 1. Okay? And so when you're, and this number here is, this is the other sum. So when I add from j is equal to 1 up to n of 1, right? That's just n. Yeah. Oh, n plus 1 there should be, huh? Yeah, n minus j plus 1 here. Let's hold on. Yeah, I messed up my sum here. So let's see. This one's this, and this is n minus, you're saying n minus j plus 1. So that would give me here, so I want n plus 1 here. So I think it's n plus 1 minus j. Okay, yeah. Yeah. So n plus 1 minus j. Like that. Okay, sorry about that. These cancel, and then you get n plus 1. Thank you. Thank you very much. Right? Thank you. All right. And so now you can pull this out because it doesn't depend on j. Right? And now when you sum 1 n times, that's the same thing as n. Okay, so this tells us that 2s is equal to n plus 1 times n, right? Which tells us that s is equal to n plus 1 times n divided by 2. All right, so that's using the summation notation. It's the exact same thing, but just with the sigma. And this, recognizing this. Okay, so, all right. So let me do another famous one. And so this is the geometric sum formula. Okay, so the theorem is as follows. So if x is an element of a field, let's say. of a field, let's say that x is not equal to, let's see. So e.g., x is an element of the reals or C, a complex number, right? So those are examples of a field. The field is just a ring, so that there's additional multiplication, and then you have multiplicative inverses, right? Then 1 plus x squared all the way up to x to the n. So this is x to the n plus 1 minus 1 over x minus 1. So I said x was not equal to 1 so that I could divide by this. That's the only reason. Okay? And then I guess I said it's an element of a field so that you have multiplicative inverses. So this is a non-zero thing. Okay, so let me do the proof of this. All right, so here's the proof. Okay, so the proof is that we'll let S be 1 plus x plus x squared plus x to the n. So this is really x to the 0 here, right? This is this sum. J is equal to 0 up to n. Okay, that's what we're doing here. So this is x to the 0 here. Also, 0 to the 0 is 1. Okay, that's another thing I should mention. So we could plug in 0 here and check this formula. So look, if we plug in 0 here, you get 1, and then this is 1 over on that side too. Okay. Okay, so notice that if we have S here, so this is, I'm just going to copy it down again. And so here's the trick. The trick is to do this. I'm just going to multiply everything times x and distribute it. Okay, and if we subtract them, right, so we have s minus xs. So if I subtract these two guys here, this goes away like so, all the way up to this one here. Right, and then we get 1 minus x to the n plus 1, since we're subtracting these two sides. So then you just solve for s, right? Right, and this tells us that here, so s is equal to 1 minus x to the n plus 1, 1 minus x. And so this is the same thing as x to the n plus 1 minus 1 over x minus 1. Okay, so that concludes the proof here. Okay, all right. So, okay, so what else do I want to say about this? Okay, so there's some other things that are interesting. So there's another theorem. Okay, and the theorem says that for any A, B in a commutative ring, so this is like completely general, A to the n minus B to the n. So this is A minus B, A to the n minus 1 plus A to the n minus 2B plus all the way up. And then it goes to up to B to the n minus 1, like so. Okay, so this is a generalization of the difference of squares formula. Squares formula. Okay, so there's kind of two ways you can do this, right? So the first proof, I'm going to give you another proof, is you can just expand it out the formula. Out the right-hand side. Okay, so let's just do that. So a minus b. And so we have this sum here, a to the n minus 1 plus a to the n minus 2b plus, and then we have here, let's add another term just to be safe. A b to the n minus 2 plus b to the n minus 1 like this. Okay, so we're going to have the thing where I multiply it by a, and then I'm going to have the thing where I multiply it by b. So this is going to be a times that stuff, and then b times that stuff. So this is a to the n minus 2 plus, or a to the n, like this, plus a to the n minus 1b plus all the way up, and then we have a squared b to the n minus 2 plus a b to the n minus 1. All right, and then we're going to have minus, and now I'm just going to multiply by b. So we have a to the n minus 1b minus a to the n minus 2b squared plus, and then it goes all the way up, right? And then it gets to here, so then it goes, or I guess minuses, minus a to the b to the n minus 1 minus b to the n. Okay? And so what you see is when you expand this out is that this cancels, this will cancel with the next term, all the way up to this canceling. So this matches all the way up to there. So we've subtracted off everything, and then all you're left with is a to the n minus b to the n. Okay, so this gives you a proof. And we didn't have to do division. We didn't have to do anything here. Okay, so this works in general. All right. So this gives you, this allows you to factor differences of powers like this. Okay. So let me give you a second proof. So the second proof is how you can remember it. So that one just is like, okay, if I'm given the formula, I have a way to verify that this is correct. Okay? But maybe you forget the formula. Okay? So if you forget the formula, what you can do is you can use the geometric sum formula. Right? Use the geometric sum formula to derive this. Okay, so here, what we'll do is, so the geometric sum formula was with, we went up to n, right? I'm going to do it with where n is equal to, say, n minus 1. So here we'll do this thing. So 1 plus x to the, I don't know, let's do m minus 1, right? So we know that this is x to the m minus 1 over x minus 1. All right, and so this tells us that x minus 1 times this thing, 1 plus x plus all the way up to x to the m minus 1. So this is x to the m minus 1. So if we let x be equal to a over b, right, then what does this give us? So this gives us a over b minus 1. And then we have 1 plus a over b plus something like this, plus a over b to the m minus 1 is equal to a over b to the m minus 1. Okay? And so if you multiply both sides of this equation, so multiply both sides, by b to the m, right? So this gives us, so here, well, we'll have a minus b. So I'm going to multiply this side by b and this side by b to the m minus 1. Okay? Then we get b to the m plus, b to the m minus 1 plus a times b to the m minus 2 all the way up to a to the m minus 1. So here I distributed this thing into two pieces, right? I multiplied this factor by b to the m minus 1 and this factor by b. And the whole thing is really multiplying by b to the m. Okay? So now this side becomes a to the m minus b to the m. Okay? So this is one way to derive it. Yeah? Or no? Okay. So, so this is another way to derive it. Here, this is kind of a cheating one here because maybe we don't have division. Or I guess we can derive this formula here, but maybe we don't have division here as well. Okay? So this proof is really not a very good proof, but it lets you derive the formula. Okay? And this proof is a better proof because we're not using division anywhere. Does that make sense? Okay. Okay. So now we have the difference of powers formula. We have the geometric sum formula. That's good. Okay. So okay. So I think I'm going to stop here, right, today, since this is where I was in the other class. And if do you guys have any questions right now? Okay. So yeah, so this gives you the two versions of the sum formula. Okay? So yeah, I'm just going to stop here. And so we're even with